right, for our last speaker of the session, we have Cameron Liang, also from IDA, but not within the sustainment group. He's an astronomer who is bringing expertise in high-performance computing, machine learning, statistics, modeling, and simulation. And today we'll be talking about high, hot, and humid on the impacts of extreme conditions on aviation.
Thank you, Rachel. So I get to say the famous line that I know I'm the person between you and lunch. So no matter how interesting this talk I am, I'm not as interesting as lunch. So I promise I'll go quick. So on the theme of aircraft and like spares, fixing aircraft, I was sitting down and it's like trying to come up with an analogy of how this relates to that. So I guess one analogy I can come up with is like, have you bought a nice hiking shoes and fix your water bottle, and on the day that you're trying to go hiking, and then it rains, and then it's like, oh, your aircraft, or you're not hiking that day. So that's sort of what the theme, or like the point of this talk would be, just to illustrate like whatever spares fixing your aircraft and all of that. That is your theoretical maximum availability of your aircraft. If there's any other external condition that render your aircraft cannot fly, then you can fly on that day. So, what is the frequencies of those events is sort of the takeaway. And the driving force of this is global rising temperature. Events that prevents you from hiking every weekend, or things that I've shown here, rare events that used to happen every once a century may happen every 10 years. So the example here is the Hurricane Sandy flooded New York subway system in 2012. That costed the city billions of dollars damage, and to prevent that, they made some investment for future possible floods. Spent about $64 million. Building a gate that prevent water from going in and other things. Just by the way, like that number is a lot smaller than the damage that it cost. So it's a worthwhile investment. Similarly, these kind of things are something that the DoD cares about. If you, even ourselves, right? Would you really want to buy a house in the beachfront in Miami in the next 50 years? What is a data-driven decision for you to do that? DoD is doing this kind of similar analysis. Where do we build our airports? Where do we, build? How long do we build our runways, and so on and so forth. So for this talk, I will focus on aviation, in particular, just the problem of ticking off. And as aircraft, experiencing a hotter and hotter climate, and it will have a more difficult time to fly. And I'll show you how and why. Okay. So 2 takeaways. If you get these 2 points after the talk, then is a win for me. Why are more extreme events more frequent? And why is the cost so high? And why should we care, therefore? So for a takeoff problem, essentially, the underlying physics is that when the air is thinner, as the jet engine takes in the air, there's less air per volume, so less dense. And the turbine and all of that has a hard time to get lift. And that's directly proportional. The force is directly proportional to the density of the air. And 3 factors: high, hot, and humid. Right? If you're in high elevation, air is thinner, it's harder to fly. You can't fly as high. And if it's hotter, also air expands. It's also then less dense. And somewhat counterintuitively, in a humid day, the air is also less dense. And that's because the water molecule is displacing the oxygen and nitrogen molecules. So by weight, which is, density is mass over volume, so there's, basically hydrogen atoms are lighter than oxygen and nitrogen. So overall, it's less dense in humid air. All right. I don't know if you have any intuitions on like, okay, the air in say 20 years, 50 years from now is slightly less dense. So what? Like what is the effect on my aircraft? How big of an effect is it? Should I really care? And to quantify this, the aviation industry and also in DoD have a metric called density altitude. It represents so the equivalent density altitude height, or in terms of feet, that the aircraft feels like it's flying compared to a standard atmosphere. If it's on a hotter day, this metric will be higher because it will be equivalent to a higher altitude, less dense air. And then if you add humidity to that, then it will be even higher, that value. So, in the future when the runway surface level condition gets hotter and more humid, then it will be essentially, this metric tells you how much harder the aircraft is going to feel to take off. I won't go through the equation how to compute this density altitude or dA, but just to emphasize, show you some quantitative changes on how it depends on temperature and humidity. So on the plot on the right-hand side here, as a function of temperature, the dry density altitude, dry dA, has some value. That's the green line, right? As you can see, if I increase the temperature, this thing rises in this manner. And then if I add in different relative humidity, that's the blue lines, and you see that it increases vertically. Basically, the whole line shift up, right? So I have some text here showing that like at the 90 degrees Fahrenheit level, a normal dry day, this density altitude value is about 2,000 feet. But if you increase the 80% humidity, a humid day, this metric goes up 500 feet extra. And that then translates to the effects on how much the aircraft is going to have a harder time to take off. And I will show you some example how this value translates to operational context, which is, I think, in the coming slides. So how do we do this? How do DoD and other the aviation industry do this? Well, they take hydrodynamic models shown here on the right-hand side, and this is showing CONUS, and on the left is the historical observations of this value. So essentially, there are stations across the world that takes measurements of temperature, humidity, and so on, and they then compute dA as a function of those two quantities and plotted the dA over time. I did here. And then there are models that trying to compute the same thing, using hydrodynamic simulations to predict the quantity. Just looking at this, you can see that they are very similar, and it's hard to sort of compare what is the quantitative differences. So in order to sort of make the quantitative, we can pick a location. Again, here I picked Miami International Airport, and then I plotted the density altitude for the moist version of this. Historical is in blue, and the projected is in the salmon red color. Overall they look very similar, so the models are sort of trustworthy, and then we understand how the atmospheric condition behave. But there are small differences in the future projected conditions. First of all, that I highlighted using a horizontal box that on the top of these two segments, what's peeking over those inside the box on the right-hand side there, the right-hand side, you can see there are more lines peeking inside the box. There are more extreme events, higher values than what the blue is doing, right? the blue, occasionally you see some tick mark going inside that high value, but the red is much more frequent. And at the same time, if you take the median or something, you can see that the average is overall higher, right? And one can understand it through simple physics. When you boil a pot of water, right, the mean temperature of that pot of water, let's say, increased by 1 degree Celsius or something, right? But all the individual molecules, atoms, have different speeds. If you take Physics 101, and there are quote unquote extreme events that happens, occasionally there's the bubble that pops up in that pot of water, and those are equivalent to those spikes, right? So as you increase the temperature of the system, not only the mean of temperature changes, but the spread of that temperature distribution also change. And it's in the tail of that distribution that extreme event happens. Just this past, I guess, year, and I'm from California, and a mean temperature increase, compared to previous year is not that much, but just occasionally there's a little bit got warmer, and then there was trigger, like one patch of dry leaves got caught on fire in the forest, and then you have wildfire, right? Okay, so those are the time series that I just showed. If you just plot them as histogram for both historical and future projected values, you see the plot on the left, bottom left here, right? There's a mean shift and the broadening of that distribution. And I sort of belabored the point about, like, okay, there's this increase of density altitude. What is the effect on aviation? So this is a rule of thumb from a paper that I found in the literature, just general. This metric actually affects different aircraft differently, because different aircraft have different engines and different shapes and so on. But in general, increase of 1,000 feet in this metric means that your engine has 3.5% or so reduction in its horsepower. And because of that, it's harder for the aircraft to get that lift. So it takes longer to climb up to a certain speed to actually take off. And therefore, that implies that your aircraft runway would have to be longer. All right, and it's longer by about 10% to maintain the current capability compared to in the future. And the landing also would have an effect, because you need to fly faster in the air for the same amount of the air is less dense, so you have to fly faster to get the same amount of lift. But as you land, because you were flying faster, that it takes extra distance for you to stop safely. All right, so this is sort of the translation from this metric dA to the effects of aircraft takeoff problem and the landing problem. So let's go into just how it changes into the future. This graphic here was inspired by the temperature spiral, if you have seen that online. So I made some similar graphic, and this is showing the mean not mean temperature, but the mean change of this metric dA over time from 2030 to 2050. As you can see that I color coded that if it's above, the delta is positive, is red. If it's below, is blue. And you can see that most of them are white, so around the mean. But occasionally, or especially towards the future, the rings gets larger and larger and larger and more red. And you can also have other features, such as in the summer and the fall, you can see the extra increase, like in this particular location, Miami Airport. November, December is experience the greatest change. All right, and we can do this for across any location on the Earth. But here I'm showing the CONUS map. This is the the median change across all at a particular month. So the top one is March, the bottom one is August, at a particular time, which is 9 o'clock UTC. And you can see that the color scale here shows summer experienced the most changes. So what it's saying is that in the future, the summer is going to get hotter. The future summer is going to be much hotter than the current summers, whereas the future spring is not as much hotter as current springs, if that makes sense. Okay, so that's just 1 month or 2 months and at particular time. Here, this plot shows what I would like to call, if I were be adventurous, a climate calendar, but I'm not adventurous, so I call it a weather calendar. This is showing on the vertical axis what month it is, and the horizontal axis what time it is of the day. And the colors again show this changes of this DA, future minus historical. And you can see for this particular location, November, maybe June and July experience the most changes across the day. Doesn't matter what time it is. All right, but so I actually another thing to point out is the sort of orders of magnitude change is about 1,400 feet increase in this metric DA, and that translates to 14% increase in runway length requirement to maintain current capability. Again, that means if this particular aircraft that you care about takes, say, 5,000 feet length runway to take off, in the future it will be 6,400 to take off. This weather conditions is diverse. So here are a bunch of different locations showing you the diversity of this effect. And for DoD and other people to make investment, or for you to, if you want to do a data-driven decision, if you want to buy a house in the beachfront or somewhere else, this is kind of the point here to show where is it be affected the most in our list. So there's the Death Valley, and then there's the Great Plains. In the Great Plains, very interestingly, around 1500s local time there, so 3 o'clock in the afternoon, and August or July, that in the summer, that's when the temperature increased the most. And it's kind of have similar effect here, but it's not as dramatic across a different location. I'm going to flash through a different location here. So the Florida area more or less looks the same as the Miami airport. And then there's also Pacific Northwest. See here. And then the Rocky Mountains. I guess midnight is really resilient. There's not much changes, but around mid-afternoon or early evening, there'll be more changes in the summer. All right, and then there's California. All right, so I can also average all these effects across the entire CONUS, and this is sort of the effect that you see on the left-hand side. I guess 2 features to point out. One is that it happens around July, August, September, October, summer and fall months. There is this rising and falling behavior that this is where it changes the most in the future. Again, the color shows you the magnitude of the change. And it goes as high as 2,000, maybe some cells are 3,000, but on average, let's say 1,400 feet, but with a strong variation. What that means is, for say I did a rough estimate of the economical impact of this effect. Just a little bit thinner air. How much is it going to cost the aviation or DoD? Because thinner air, your engine, has to loses power, so that you cannot carry, say, as much weight So instead of carrying like people or cargoes, you carry more fuel. You have to buy more fuel to do the same mission. And using this estimate, 2023, about 10 million commercial flights within the CONUS itself. On average, 1,500 gallons of fuel per flight. At $3 per flight per gallon, you did the math here, $45 billion. So 5 reduction in weight means those weights will be going to fuel instead of carrying cargo, and that is $2.25 billion a year. Right, a tiny change in the atmospheric condition can cause billions of dollars every year. All right, this is my summary. I'll leave it up here. Happy to take questions. Thank you.
Yeah, so now it's my turn to keep you guys from lunch. Okay, no, I really like that presentation. What kind of modeling did you end up doing? Was this like a REMA forecast or like a simple linear kind of model?
Yeah, so the model, I did not talk about the model itself at all, and the model itself is very, very complicated as well, beyond my ability to do that, and it requires supercomputers to do so. And these are hydrodynamic simulation, if I may say the word, climate models, and that is a career in and of itself. Yeah.
Gotcha. Thank you.
Yeah.
Thank you. Great talk. I was wondering if any of the runway concerns have been communicated to any agencies, like, because there are definitely, it's known that there are some airports that are very difficult to land at already, and to know that the runway demands are going to make it harder for certain aircraft, for instance, to be able to fly there in the future would be definitely good to know about.
Yeah, great question. And IDA has been developing this capability and building up this capability to answer questions exactly like that. So we have been working with various DoD sponsors to answer that question. Not only in terms of like where the runway is and what it is that we have to do, but also identifying vulnerable runways for different COCOMs. There are runways that are built on mountains that don't have a lot of like space to work with already. So should you relocate? Should you like build different aircraft to adapt this change? Not only that, but IDA really has in the past few years, led by Dr. Jen Billy, to tackle this question. For basically all these changes, not just aircraft, but also like infrastructure. If you build a building that you expect to be really hot or really humid, or there's a lot of storm, you want to build it differently than you build it today. So we need to understand how these models are projecting in the future and how we can adapt to it.
Sorry, I'll be quick. So this is the temperature effects. Are you also looking at wind and weather patterns? Because airports generally are aligned for optimization of wind to also account for safety and length and recovery distance. So is that like another layer of this?
Yeah, exactly. Great question. We have looked at wind, and wind is a complicated thing to model. And there are things that you should trust from a climate model. There are things that you should not trust climate models. Some predictions are better than others. In the case of wind, you're basically modeling turbulence of at the scale relevant to the size of the aircraft. Whereas most of these simulations, despite the highest simulation of these models to date, they are not at the resolution of aircraft itself. So we are not really resolving the directions of wind and all of that. So that is a complicated modeling task. You require super, super high resolution and super, super high time resolution in spatial and time. So that is a study that we sort of like kind of, let's just focus on the easy one to make the prediction. Another thing that we sort of not argue away, but like maybe other simpler adaptation to wind is that, you know, if you are windy in one direction, you can just turn your plane around and like in the direction of the takeoff, turn your plane around, go to the tail of that runway and take off the other direction. But there are issues like crosswind that is going to be a problematic that we have not